In this section, we will discuss the steps involved in a typical lithography process. First, you must start with a clean substrate. Perform a cleaning step that is compatible with your substrate materials. If you don't clean first, any particles on the substrate will get stuck to your sample during the coating process and get carried through the rest of your process steps. This could negatively impact your device if the particle is in a critical area, so start each process with a thorough cleaning. The next steps are priming, coating, and soft baking. In the prime step, you prepare the sample surface for coating. The spin coat step is done to coat your sample with photoresist. Then the soft bake step removes the remaining solvent and hardens the photoresist. We will discuss each of these three steps in more detail in the next few slides. The priming step is performed to ensure good adhesion between the sample and photoresist. Many substrate materials, including silicon dioxide and silicon with a native oxide layer, are hydrophilic and tend to absorb water from the air. Photoresist is hydrophobic, so hydrophilic surfaces must be treated to improve adhesion. First, the sample is baked to drive off as much water from the surface as possible. Then a chemical is added to produce a hydrophobic monolayer on the sample surface. Once the priming step is complete, the substrate is ready for photoresist application. During the spin coat step, liquid photoresist is dispensed onto the wafer and spun to the desired thickness. Here we'll see a typical spin coat process on an automated photoresist coat track. First, the wafer starts spinning, and the nozzle dispenses photoresist onto the wafer. The wafer continues to spin as the resist spreads to the edges. Then the spin speed is increased, and the photoresist continues to spread into a uniform layer. Most of the solvent is driven out of the photoresist during the spin step, which turns the photoresist from a liquid to a solid. Next, the nozzle moves back over the wafer to remove the edge bead that forms during the coat process. The nozzle dispenses a thin stream of solvent just along the edge of the wafer to remove the photoresist that has built up there. Lastly, the wafer is spun dry. This graph describes the spin speeds during the coat process in more detail. During the dispense step, the wafer is spun slowly so the resist can spread and cover the sample surface. During the ramp step, the speed is increased to reach the spin step speed. This ramp rate can be high for thinner resists, but may need to be lower for thick resists to ensure good coat uniformity. In the spin step, the resist thickness is set. A slower speed yields a thicker resist layer, and a faster speed yields a thinner resist layer. This graph shows spin curves for three different photoresists. The graph is created by plotting the photoresist thickness versus the spin speed during the spin step. These plots are used to find the appropriate spin speed for the desired photoresist thickness. Different photoresists with different viscosities will have different spin curves and different thickness ranges. The yellow line is from a photoresist with high viscosity, while the red and blue lines are from lower viscosity resists. During the spin coat step, an edge bead forms as photoresist piles up on the edge of the sample. If the sample is then placed in contact with a mask, there will be a gap between the critical area on the sample and mask. This gap can make the features appear out of focus when printed on the sample. On a photoresist coat track, the edge bead is chemically removed with a spray nozzle, as we saw earlier. On a manually coated sample, the edge bead can be chemically removed with a solvent-soaked Q-tip or exposed and developed away. After spin coating is complete, the soft bake step is performed to remove most of the remaining solvent and set the final photoresist thickness. After the sample is coated in photoresist and soft baked, it is selectively exposed to light. This is the pattern transfer step. During exposure, the photoresist undergoes a chemical transformation in the areas exposed to the light. More information about the exposure step will be explained in the next section. After exposure, the sample is post-exposure baked and developed. The post-exposure bake is performed to complete the chemical conversion process and can be optional depending on the photoresist used. During the develop step, a chemical reaction between the photoresist and developer reveals the pattern. Either the exposed or unexposed regions remain, depending on the tone of the photoresist. This diagram depicts a positive tone photoresist, where the exposed region is removed by the developer. On a track system, the develop, rinse, and dry steps are automated. First, the nozzle sprays the wafer with chemical developer. This is done to wet the sample surface, and without it, the developer would flow off the wafer. Next, a stream of developer is dispensed to form a puddle on the wafer. The sample sits in this developer puddle for a set amount of time. The time should be long enough to completely dissolve the soluble photoresist, but not too long, or the pattern may become overdeveloped. After the puddle step, the wafer is spun and rinsed with water to remove all the developer. Lastly, the wafer is spun dry. After developing, you must inspect your samples. There may be a bit of residue left in the areas you want to be cleared, and a quick extra 10 seconds in developer could improve your pattern. This is the last step where mistakes can be corrected easily, so be sure to check at this point before moving on. After a sample is developed, it may appear fully cleared in the open areas, but actually has photoresist residues on the sample surface. During the DScum step, an oxygen plasma is used to remove any remaining photoresist residues that can't be seen by eye. DScum is not required, but may be important in processes such as liftoff, where you want the deposited material to adhere well to the substrate. DScum should not be performed on samples with visible residues. If you do notice a residue after developing, you may need to adjust your exposure or develop time. DScum will not be sufficient in this case. The final step in lithography processing is the hard bake step. The hard bake is performed to further harden the photoresist. This step can be critical to etch processes as it greatly improves the selectivity of the etch. In the plasma etch tools at the NanoLab, the hard bake step is required to ensure the etch chambers remain clean. This is the end of video 2. In the next video, we will discuss the photolithography exposure process.